What if I told you the moon, an airless world, has been caught rusting? Not as a joke, not as a headline trick. Actual iron oxide chemistry, a mineral called hematite, the kind of rust you'd normally associate with oxygen-rich environments. And the part that makes this feel impossible is simple. The moon is about 384,400 kilometers away. It doesn't have an Earth-style atmosphere full of free oxygen. And yet orbital spectral data has shown signatures consistent with hematite, especially toward the poles, and stronger on the side of the moon that faces Earth. So the question isn't, can rocks contain oxygen? Lunar rocks absolutely contain oxygen, locked into minerals. The question is, how do you get oxidation that looks like rust on a world that, on paper, should be terrible at rusting? Because rust, real rust, normally needs a few ingredients to line up. You need iron. The moon has plenty of that in its surface materials. You need oxygen involved in the reaction. You also usually need a chemical pathway that's helped along by water or hydroxyl, even if it's just trace amounts on grains. And the moon seems to be missing the easy version of all of that. No thick oxygen atmosphere, no rain, no rivers, no humid air quietly doing chemistry in the background. And then there's a fourth ingredient that makes the moon feel even less compatible with rust: the solar wind. The solar wind is a stream of charged particles coming off the sun, and it's especially rich in hydrogen ions. Hydrogen doesn't help rust. In many surface reactions, hydrogen can work against oxidation by chemically reducing oxygen-bearing materials. If you had to pick a constant environmental pressure that makes building up oxidized minerals harder, the solar wind is high on the list. So if the moon is rusting, something has to be changing the rules. Either by delivering oxygen in an unusual way, by providing a rare chemical helper like OH, where we didn't expect it, or by turning down the solar wind's ability to erase oxidation long enough for rust-like products to accumulate. This is where the pattern in the data becomes the clue. The result that kicked off this wave of attention came from NASA's Moon Mineralogy Mapper, M3, a spectrometer that flew on India's Chandrayaan-4 One mission, MM3, didn't photograph rust. It measured reflected light across many wavelengths, looking for mineral fingerprints that match known materials. And in 2020, a team led by Shuai Li published an analysis in Nature Astronomy reporting widespread hematite signatures at high latitudes. That finding is already weird, but what makes it feel like a detective story is that the signal appeared stronger on the near side, the side that faces Earth, than on the far side. If that's real, it's hard to shrug off as purely random or purely local. It suggests geometry matters, which immediately suggests Earth might matter. Because Earth isn't just a planet next door. Earth is a magnetized world with a giant magnetic environment that reaches far into space. The solar wind hits Earth's magnetic field and stretches it into a long tail on the night side, the magnetotail. And the moon doesn't always live in the raw solar wind. For a few days each month, around the time of full moon, it passes through Earth's magnetotail, and that changes the particle environment around the moon. Inside the magnetotail, the solar wind is altered, and Earth-origin ions can be present, particles that ultimately come from Earth's upper atmosphere and get swept into Earth's magnetic system. This isn't just a convenient story. Space missions have observed oxygen ions of terrestrial origin reaching the moon when it passes through Earth's magnetotail. So now the impossible rust problem becomes a very different question. What happens if the moon gets brief, repeated exposures to Earth-sourced oxygen ions, while also spending that time in a region that can reduce the direct impact of the solar wind? You can see how the chemistry window could open. Imagine trying to paint a wall, but someone keeps wiping it clean every minute. That's the moon under constant solar wind bombardment. Oxidation products have a hard time building up, but once a month, the wiping slows down. Not to zero, but enough. And at the same time, a new ingredient, oxygen ions, shows up more strongly than usual. If there are trace hydroxyl groups on surface grains, or if polar regions have access to water ice chemistry nearby, or if local conditions help oxygen stick, you can start forming hematite over long timescales. That's the first major explanation. Earth's oxygen, delivered down the magnetotail, helps oxidize lunar surface iron into hematite, especially at higher latitudes and more strongly on the Earth-facing side. But that's not the only plausible route, and this is where the mystery deepens instead of ending. Because the moon is also a constant impact laboratory. Micrometeorites hit the lunar surface all the time. Each tiny impact is a short-lived furnace. Local melting, vapor, shock chemistry, then rapid cooling. In those microenvironments, you can create reactive compounds and lock them into glassy or altered surface materials. This creates a second possibility. Some portion of the rust-like signal could come from local chemical processing. Impact-driven reactions involving oxygen already present in minerals, plus whatever transient oxygen or OH is available in the near-surface environment. It wouldn't look like Earth's slow, wet corrosion. It would look like chemistry in bursts, preserved in the regolith. And then there's a third idea that sounds subtle, but matters. Even if Earth isn't providing most of the oxygen, Earth could still be enabling oxidation simply by changing the balance of incoming particles. If being in the magnetotail reduces the solar wind's hydrogen bombardment, then it reduces the surface's constant anti-oxidation pressure. That alone could let oxidation products accumulate more easily, especially in places where temperature and volatile chemistry favor it. So you end up with a three-part explanation set that actually fits what we see as a pattern rather than a one-liner. Earth may be supplying oxygen ions during magnetotail crossings. Impacts may be creating localized chemistry that produces oxidation products. Earth's magnetotail may temporarily reduce the solar wind's ability to chemically erase oxidation. Here's what makes those explanations satisfying. They're not just stories. They make predictions. If Earth oxygen delivery is important, you'd expect correlations with magnetotail exposure and a near-side bias. If impact chemistry dominates, you'd expect a different distribution, less tied to Earth-facing geometry. If shielding is the main driver, then solar activity and magnetotail conditions should modulate how strongly oxidation products can build up over time. But just when the mystery feels solvable, you hit the second twist. The phrase oxygen on an airless world is dangerously easy to misunderstand. The moon isn't lacking oxygen in the way a vacuum chamber lacks oxygen. Lunar rocks are packed with oxygen atoms, bound into silicates and oxides. What the moon lacks is a thick, circulating atmosphere with abundant free oxygen doing chemistry everywhere. So the real puzzle isn't whether oxygen exists. It's whether oxygen is being delivered, mobilized, or made chemically available in the right way to drive the specific oxidation signature we're calling rust. And there's another complication. Spectroscopy is powerful, but it can be tricky. M3 identifies minerals by spectral fingerprints, but the moon's surface is not a clean sample tray. It's space-weathered, mixed, glassy in places, and constantly churned. Different mixtures and alteration states can sometimes mimic similar features. especially when you're interpreting subtle signals across complex terrain. That means one live debate is whether the signal is hematite everywhere, or whether it's a mix of materials producing hematite-like signatures under lunar conditions. Add to that the moon's extreme environmental variation, temperature, sunlight angle, and volatile availability shift hard with latitude, and it becomes entirely plausible that more than one pathway is operating at once. Some oxidation might be Earth-assisted, some might be impact-driven, some might only stick when the magnetotail changes the particle environment, which leads to the strangest and most interesting conclusion. The moon may not be a dead, isolated rock at all. It may be a chemical recorder of the Earth-Sun environment it travels through, reacting slowly, repeatedly, in a monthly rhythm we're only now learning how to read. So I genuinely want to know what you think. Which explanation feels most convincing right now? A. Earth oxygen delivered down the magnetotail. B. Micrometeorite-driven local chemistry. C. The magnetotail mainly acting as a shield that lets oxidation finally accumulate. Drop A, B, or C in the comments and tell me why. I read them, and I'm curious which clue you think matters most. Because this isn't just a fun lunar oddity. It changes how we think about airless worlds across the solar system. If Earth can influence the moon's surface chemistry at a distance, other planet-moon systems could be chemically linked too, especially around magnetized planets. And it matters for exploration, because the moon is where we're trying to build the next era of human activity off Earth. Understanding surface chemistry affects how we map resources, how we think about dust interactions, how volatiles move, and what stable really means on an exposed surface. It also hints at something almost poetic. The moon might preserve a long-term record of Earth's atmospheric escape, like a geological hard drive parked next door, collecting traces of Earth's influence over enormous stretches of time. The good news is that this mystery is testable. Better maps, better correlations with space weather conditions, and, most decisively, direct measurements and samples, especially near the poles, can tighten the interpretation fast. This isn't a "we'll never know" story. It's a "we just learned what to measure" story. And this isn't the only weird chemistry happening on worlds we label dead. The moon also has water-related surface chemistry tied to the solar wind, lunar dust that behaves in electrically strange ways, and other airless worlds, like Mercury, that keep surprising us. So if the moon can rust without air, imagine what else we've been missing in plain sight. Stay curious, and I'll see you in the next one.